Assalamu alaikum. Bismillahir-Rahmanir-Rahim. I welcome you to the 29th lecture for the series of lectures on advanced computer architecture. Today, we will continue with our discussion on to the memory hierarchy design with focus on to the cache performance enhancement by reducing cache miss penalty. Last time, we talked about 4 basic questions which a cache memory designer usually asks. These 4 questions are: number 1, the block placement, where a designer is concerned about where can a block be placed in the upper level or in the cache memory. The second question is regarding the block identification, where a designer wants to know how is a block found if it is in the upper level cache or not. And the third question deals with the block replacement, that is, which block should be replaced when a miss occurs. And the fourth question is regarding the write strategy, which deals with what happens on write. Now, while talking about the cache write strategies, which are the write back strategy and write through strategy, we also discussed the use of an additional buffer known as the write buffer. This buffer is used to enhance the overall performance of the memory. However, while talking about the use of the write buffer, we noticed that the write buffer gets saturated when the frequency of store with respect to the time approaches beyond the DRAM write cycle time. And we also found that in this situation, either write back approach is used or a level 2 cache is introduced in between the level 1 cache and the DRAM or the main memory. At the end, we discussed the write miss policies. These policies are the write allocate policy and no write allocate policy. We studied that the write allocate policy is one where a block is allocated in the cache on a write miss. That is, the block to be written is made available in the cache. Whereas the no write allocation policy is one where the blocks stay out of the cache until the program tries to read the block. That is, the block is modified only in the lower level memory. So with this much discussion on to the write strategies, today we will talk about the impact of caches on the CPU performance. We have already talked about the CPU performance, and we noticed that the CPU performance can improve using memory hierarchy as it offers high access speed through the use of principle of locality. Now today, to evaluate the CPU performance vis-a-vis cache performance, we will rewrite the CPU execution time expression in terms of the memory stall cycles. The expression appears to be as shown over here. That is, the CPU execution time is equal to the sum of CPU execution clock cycles and memory stall cycles multiplied by the clock cycle time. Here we assume that the hit clock cycle is included in the CPU execution clock cycle. Now, in order to see the impact of caches onto the CPU performance, let us consider this example of an in-order execution computer program and see the impact of the caches on the CPU execution time. Here we assume that the cache miss penalty is 100 clock cycles. All instructions normally take 1 clock cycle and the average miss rate is 2%. Then if we assume that the average memory references per instruction is equal to 1.5 and average number of cache misses per 1000 instructions is 30, then let us find the impact of cache on performance of the CPU by considering both the misses per instruction and the miss rate. For this, we can find out this value by considering our expression for CPU time, which is equal to the CPU execution clock cycles plus the memory stall cycles, both multiplied by the clock cycle time. Now, substituting the values which are given in this example, we can find out that the CPU time with cache, which includes the cache misses, is equal to the instruction count multiplied by the 30 divided by 1000, which is in fact the number of cache misses per 1000 instruction, multiplied by 100, which is the cache miss penalty, and whole multiplied by clock cycle time. And this results in a value which is equal to instruction count multiplied by 4 clock cycles time. We can also find out the CPU time with cache, that is including the miss rate, as it is expressed over here, equal to instruction count multiplied by 1, which is the hit rate, plus 1.5 multiplied by 2%, and all these values multiplied by 100. So this whole again gives us the instruction count multiplied by 4 clock cycles per time. This shows that the CPU performance with cache increases 4 times as compared to the CPU time without cache. Here we have observed the impact of caches on the CPU performance based on the cache misses and the miss rate. Whereas the cache performance can be defined in terms of the memory stall cycles, which in fact depend on number of misses or the miss rate and cost per miss, or say the miss penalty. Memory stall cycles equal to the sum of instruction count multiplied by reads per instructions multiplied by read miss rate multiplied by the read miss penalty plus the instruction count multiplied by write per instruction multiplied by write miss rate multiplied by write miss penalty. Or we can rewrite this expression for the memory stall cycles as number of reads multiplied by read miss rate multiplied by read miss penalty plus number of writes multiplied by write miss rate multiplied by write miss penalty. Now, averaging the read and the write miss rate memory stall clock cycles can be expressed as it is equal to the number of memory accesses multiplied by miss rate multiplied by the miss penalty. Now, in order to understand this concept, let us assume that there is one cycle to hit the cache, then the number of memory accesses is equal to the hit time and the average memory access time is equal to the hit time multiplied by the misses rate multiplied by the miss penalty. Note here that the average memory access time is an indirect measure of the CPU performance and is not a substitute for the execution time. However, this expression can decide about the split caches, that is, the instruction cache and the data cache or the unified cache. For example, if we have to find out which of these two types of caches, that is, the split caches and the unified caches, has lower miss rate, we can use this formula in this example over here. Now, let us consider a 32 KB unified cache with misses per 1000 instructions equal 43.3 and instruction or data split caches equal to 16 KB with instruction cache misses per 1000 as 3.82 and data cache misses per 1000 equal to 40.9. Here, let us assume that 36% of the instructions are data transfer instructions and 74% of the instructions are the memory reference instructions. Also, we assume that the hit takes one clock cycle where the miss penalty is 100 cycles and a load or store takes one extra cycle on unified caches. Assuming write-through caches with the write buffer and ignoring stalls due to the write buffer, let us find out the average memory access time in each cache. Note that in order to solve this problem, we first find the miss rate and then the average memory access time. So let us first of all find the miss rate. We know that the miss rate is equal to the misses per 1000 divided by the accesses per instruction. And for 16 KB instruction cache, the miss rate for this example is equal to 3.82 divided by 1000 whole divided by 1, which is the accesses per instruction, and this results in a value equal to 0.0038, whereas the miss rate for the 16-bit data cache using the same expression comes out to be equal to 0.114. As about 74% of the memory accesses are instructions, therefore the overall miss rate for split caches is equal to 74% multiplied by the miss rate for the instruction plus 26 multiplied by the miss rate for the data caches, and this results in a value which is equal to 0.0324. And now let us find out the miss rate for 32 KB unified cache, which is equal to 43.3 divided by 1000 divided by 1 plus 0.36, which is equal to 0.318. This shows that the unified cache has slightly lower miss rate as compared to split caches. Now let us find out the average memory access time. The average memory access time is equal to the sum of access time for the instruction memory and the memory access time for the data memory. The memory access time for instructions is equal to the percent instructions multiplied by the sum of hit time and the instruction miss rate multiplied by miss penalty. Similarly, the data access time is equal to the percent data multiplied by sum of hit time and the data miss rate multiplied by miss penalty. So, by using this expression for the average memory access time and the data provided in this example, the average memory access time for the split caches is equal to 4.24 and for the unified cache is equal to 4.44. That is, the split caches have slightly better average access time and they also avoid the structural hazards. Therefore, usually the split caches are preferred over the unified caches. Now, from our discussion on the CPU and the cache performance, we may conclude that the average memory access time gives us the basic framework to optimize the cache performance and hence the CPU power. Therefore, the average memory access time formula, that is, the average memory access time equal to the hit time plus miss rate multiplied by the miss penalty, suggests us different options to improve the cache performance. There are 4 basic options based on this formula, and these 4 options are that in order to improve the cache performance, we may reduce the miss penalty, or we may reduce the miss rate, or reduce the miss penalty or miss rate via parallelism, and the last one is reduce the time to hit in the cache. Now, today we will discuss different techniques to reduce the miss penalty. There are 5 different techniques which are used to reduce the miss penalty. These techniques are the use of multi-level caches, The second technique is critical word first and early restart. The third technique is to give priority to the read over the write misses. The fourth one is to merge the write buffers. And the last one is to introduce a victim cache. Now, let us consider the first technique, that is the multi-level caches. This technique ignores the CPU, but it concentrates on the interface between the cache and the main memory. The basic idea of this technique is that we use multiple levels of caches. Here, based on the trade-offs between the cache size, that is the cache effectiveness, and the cache cost, that is the access time, a small, fast memory is used as level 1 cache, although the concept of adding another level of cache in the hierarchy is simple, but it complicates the performance analysis. In order to study the multi-level cache's performance, let us determine the expression for the average access time for multi-level caches. We know that the original formula for average access time is that the average access time is equal to the hit time for level 1 plus the product of the miss rate and miss penalty for level 1, where the miss penalty for level 1 is indeed equal to the hit time for level 2 plus the product of miss rate and miss penalty for level 2. Now, combining these two, we can find out the average memory access time equal to the hit time for level 1 plus miss rate for level 1 multiplied by the sum of hit time for level 2 and the product of miss rate and miss penalty for level 2. And the average memory stalls per instruction for multi-level caches can be determined by expanding this expression for memory stalls per instruction, including the impact of the second level cache. So we can rewrite this expression as the stalls per instruction on the average equal to the misses per instruction for level 1 multiplied by the hit time for level 2 and the misses per instruction for level 2 multiplied by the miss penalty for level 2. In these expressions for average access time and average memory stalls per instruction, the miss rate of level 2 cache is measured on the leftover from the level 1 caches. So this shows that there is some difference between the miss rate for level 1 and level 2 caches. We can distinguish the miss rates for these two levels by defining these two new terms, that is the local miss rate and global miss rate. The local miss rate is a measure of misses in cache divided by the total number of misses in this cache for which we want to find out the miss rate. So this shows that the miss rate of the level 1 cache or the miss rate of the level 2 cache is defined as the local miss rate, whereas the global miss rate is measure of the number of misses in the cache divided by the total number of memory accesses generated by the CPU. Now, by this definition, the global miss rate of first level cache is equal to the miss rate of level 1 cache, whereas the global miss rate of the second level cache is equal to the miss rate of level 1 cache multiplied by the miss rate of level 2 cache. Here, note that the local miss rate for the second level cache is large because the first level cache absorbs maximum memory accesses. Hence, the global miss rate is more useful measure as it indicates the fraction of the memory accesses from CPU that goes all the way to the main memory. In order to understand the use of local miss rate and global miss rate, let us consider an example where we want to find the local miss rates and global miss rates. Also, we want to find the average memory access time and average memory stalls per instruction. Let us suppose that it is given that for 1000 references with 40 misses in level 1 cache and there are 20 misses in the level 2 cache. Here we also assume that the miss penalty for level 2 cache is equal to 100 clock cycles. The hit time for level 2 cache is equal to 10 clock cycles. The hit time for level 1 cache is equal to 1 clock cycle, and there are 1.5 memory references per instructions. Now, to solve this problem, let us look into the solution for this problem. Here, the miss rate for either local or global L1 cache is same and it is equal to 4%, which is determined 40 divided by 1000 multiplied by 100. Whereas the local miss rate for level 2 cache is equal to 20 divided by 40 and it is 50%. Whereas the global miss rate for level 2 cache is equal to 2%, which is determined as 20 divided by 1000 whole multiplied by 10. We can substitute these values into the expressions for average memory access time, which we have already determined, and it results in a value for average memory access time to be equal to 3.4 cycles. Now let us find out the average memory stalls per instruction, which is in fact the measure of the miss penalty. The average memory stalls per instruction is equal to misses per instructions for L1 cache multiplied by the hit time for L2 cache and the misses per instruction for L2 cache multiplied by the miss penalty for L2 cache. Now, for the memory references per instruction equal to 1.5, this gives us that the misses per instruction for level 1 cache is equal to 60% per 1000 instructions, and for L2 cache is equal to 30% for 1000 instructions, which results in the average memory stalls per instruction to be equal to 3.6 clock cycles. That is, the average miss penalty using multiple level caches reduces by a factor of 100 divided by 3.6, which is approximately equal to 28, and this much reduction is with relative to the single level cache. This example shows the impact of combined read and write on the average memory stalls or miss penalty, assuming write back first level cache. Now let us see how the miss rates and relative execution time change with the size of the second level cache. For this purpose, the figure here shows miss rate versus cache size for multi-level caches. In this figure, the miss rate of single level and multi-level, that is the local as well as global caches versus cache size, is plotted. Here the L2 unified cache is assumed to be two-way set associative with least recently used replacement policy. Note that the miss rate of global level caches and the single level caches is identical, but the local level caches have extensively high miss rate for smaller sizes. The local cache plot here to the left of the blue line shows that the cache sizes less than 64K byte has very high miss rate, which ranges from 88% to 98%, whereas the miss rate rapidly reduces for cache sizes greater than 128K byte. From these figures, we may conclude that the average miss rate can vary by changing the size of first level cache. The second level cache should be much larger than the first level cache because the global cache miss rate is similar to the single cache miss rate. Also note that the prime difference between the two levels is the speed of caches at each level. The speed of first level cache affects the clock rate of the CPU, whereas the speed of second level cache only affects the miss penalty of the first level cache. With this much discussion onto the multi-level caches to reduce the miss penalty, let us consider the second technique, that is the critical word first and early restart. The basic concept of this technique is do not wait for full block to be obtained and loaded into the cache before restarting the CPU. The CPU normally needs one word of a block at a time. Thus, it does not have to wait for the full block to be loaded before sending the requested word and restarting the CPU. Whereas the concept of early restart says that request the word in a block in normal order. As soon as the word of the block arrives, send it to the CPU and let the CPU continue execution. Whereas from critical word first, we mean that request the missed word from the memory first, and the memory sends it to the CPU as soon as it arrives. Using these concepts, the CPU continues filling the rest of the word in the block afterward. Now, in order to understand the basic concept of critical word first and early restart, consider a computer using 64-byte or 8-word cache blocks, and an L2 cache takes 11 clock cycles to get the first 8 byte, that is the first word or the critical word, and then it takes only 2 clock cycles per 8-byte word to get the rest of the block, and 2 issues per cycle are assumed. Here we can calculate and compare the average miss penalty in case of number 1 with critical word first, assuming no other access to the rest of the block when the critical word is accessed, and second, without critical word first, that is assuming following instructions read data sequentially 8-byte word at a time from the rest of the block. That is, the block load is required in this case. To solve this example, let us see how we can find out the average miss penalty in case of critical word first. The average miss penalty is given as the miss penalty of the critical word plus the miss penalty of the remaining words of the block. This is equal to 11 multiplied by 1 for the critical word and 2 multiplied by 7 for the remaining 7 words, and it is equal to 25 clock cycles. Whereas the average miss penalty without critical word first, which also requires a block load, the total average miss penalty is equal to 25 plus 8 divided by 4, which is corresponding to 2 issues per cycle. So 4 cycles for 8 issues in this particular case, and this gives us a total value of 29 clock cycles as the miss penalty in case of without critical word first. So this example shows that the benefit of critical word first and early restart depends on the size of the block and the likelihood of another access to that portion of the block that has not been fetched. So this method has got some merits and demerits. The merit of this technique is that it does not require extra hardware. The drawback of this technique is that it generally uses only large blocks. Therefore, the programs exhibiting special locality may face a problem in accessing the data or instructions from the memory, as the next miss is to the remainder of the block instead of to the first or the critical word. So this gives us the general concept of critical word first and early restart. However, this technique is quite useful in reducing the miss penalty. Now, let us consider the third technique, that is priority to read miss over the write miss. This technique reduces the average miss penalty by considering the overlap between the CPU and cache miss penalty. We have already discussed how the write buffer reduces the write stalls in write-through caches. The write buffers ensure that the write to the memory does not stall the processor. Furthermore, the write buffer may hold the updated value of a location needed on a read miss, and the processor is blocked till the read returns. Thus, the write buffers do complicate the memory accesses and need consideration. For this purpose, let us consider an example program segment and discuss how the complexities of write buffer can be simplified by giving priority to read misses over the write misses. For this purpose, let us consider this code shown over here, where the first instruction is a store instruction and the second and the third instructions are the load word instructions to a location which is 512 or 1024. Here we assume that the code is implemented using a direct mapped write-through cache that maps 512 and 1024 bytes to same block, and forward write buffer is assumed. So let us find if value in R2 always be equal to the value in register R3. Note that this is the case of a read after write data hazard. Now let us see how the cache access is performed. Here, the data in R3 register is placed in the write buffer after the first instruction, that is, after the store instruction, which uses index value of 512. The following load instruction, that is the second instruction in sequence, uses the same index, that is 512, and therefore it results in a miss. The second load instruction, that is the third instruction in sequence in this program segment, tries to put the value in location 512 into the register R2. This also results into a miss. Now, if the write buffer has not completed writing to the location 512 in the memory, the read of location 512 will put the old value into the cache and then into the register R2. Thus, the register R3 would not be equal to the register R2. This is because the reads are served before write have been completed. That is, the write through with the write buffers offer read after write conflicts with the main memory, reads and the cache misses. And if the processor simply waits for write buffer to empty, it might increase read miss penalty. Say for old MIPS 1000, it may be increasing by 50%. The simplest way to overcome this dilemma is to give priority to the read. That is, either wait for write buffer to empty or check write buffer contents on a read miss, and if there are no conflicts and memory system is available, then let the memory access continue for read. Note here that by giving priority to read miss, the cost, that is the penalty of write by the processor in the write back register, can also be reduced. In write back caches, the read miss may require replacing a dirty block, which is normally done by writing dirty block to the memory and then do the read. Whereas the write back cache can also have a better alternative to copy the dirty block to a write buffer, then do the read and then do the write. So this shows that by giving priority to the read miss over the write miss, the CPU stalls less because it restarts as soon as the read is done. Hence, this technique reduces the miss penalty. Now, with this much discussion on to the third technique, let us consider the fourth method to reduce the miss penalty. The fourth method is referred to as merging the write buffer. Here, in order to discuss this, we know that the write-through cache rely on write buffer, as all stores must be sent to the lower level of the hierarchy. Even the write back caches use a simple buffer when a block is replaced. In normal mode of operation, the write buffer absorbs write from the CPU and it commits to the memory in the background. However, here the problem is that small write buffer may end up stalling processor if they fill up and the processor needs to wait till write committed to the memory. This problem is resolved by merging cache block entries in the write buffer, because we know that the multi-word writes are usually faster than the writes performed on one word at a time. Moreover, the write usually modifies one word in a block. Thus, if a write buffer already contains some words from the given data block and we will merge the current modified word with the block parts already in the buffer. That is, if the buffer contains other modified blocks, the address can be checked to see if the address of this new data matches the address of valid write buffer entry. Then, in this particular case, the new data are combined with the existing entry, it is referred to as the write merge. Note that here the CPU continues to work while the write buffer prepares to write the word to the memory. This technique, therefore, reduces the number of stalls due to write buffer being full. Hence, it reduces the miss penalty through improvement in efficiency of the write buffer. In order to explain this, let us consider a 4 entries write buffer shown here with each entry to hold 4 64-bit words. Here, 4 stores, say at memory addresses 100, 108, 116, and 124 would fill the buffer at 1 word per entry at a sequential address. Here, the buffer is full even though 3/4 of each entry is wasted. Note that here the address for each entry is on the left with the valid bit V indicating whether or not the next sequential 8 bytes are occupied in this entry. Whereas with the optimization using write merge, these 4 words fit within a single entry as shown over here. Thus, it enhances the overall performance of the memory by reducing the miss penalty. Another way to reduce the miss penalty is to use a victim cache which remembers what was discarded. This information is remembered because it may be needed again. This method reduces the miss penalty because the discarded data has already been fetched, so it can be used again at a small cost. The victim cache contains only discarded blocks because of some earlier misses and are checked on another miss to see if they have the desired data before going to the next lower level memory. If the desired data or instruction is found in the victim cache, then the victim block can be swapped. The recycling requires small, fully associative cache between a cache and its refill path called the victim cache as shown in the following figure. The victim cache here is aimed to reduce the damage done by the conflict misses. Basically, we can see that in 1990, Juppy found that 4-way victim cache reduces conflict misses by 20% to 95%, especially for small, that is 4K byte direct map caches. So this shows that victim cache is a very useful method to reduce the miss penalty in case of conflict misses. So today we have discussed 5 different techniques to reduce the miss penalty. With this much discussion, we stop here, and next time we will take up different methods to reduce the miss rate or to reduce the hit time. Till then, Allah Hafiz.